next up, we have Sagar and Alexandre from Funding Circle, who are going to be taking us through a talk. But for those people who don't quite know about Funding Circle, haven't heard of them before, a quick introduction about the company. So Funding Circle is one of the largest online small business loans providers and one of the best capitalized lending platforms in the world. Their backers collectively manage over $5 trillion and are the leading firms behind Facebook, Twitter, Skype, and Betfair. So some successful competition there. And over the last 10 years, they have built a machine learning and technology platform that is revolutionizing how small businesses access finance. And now business owners can complete a loan application and receive a decision in a matter of minutes on their platform, enabling them to get funding quickly and at an affordable rate, which is fantastic. Sagar is a senior software engineer at Funding Circle who loves to break apart and build things. And Alexandre Mendes, also a senior software engineer at Funding Circle, has been working on servicing their front end since 2021. Which brings us on to their talk, which is going to be about how they're using CQRS and Micro frontends to build their new borrower portal. So Sagar and Alexandre, would you like to introduce yourselves, and then we can kick off with your talk.
Sure, Henry. Thank you very much.
Thank you, Henry. Yes, my name is Alexandre. I am a front-end developer at Funding Circle, working on the servicing side of the business.
Hello, everyone. My name is Sagar, and I work with Alex on the loan servicing side of things. I've been at Funding Circle since 2019. If we go to the next slide. So, yeah, as Henry said earlier, at Funding Circle, we help small businesses get the funding they need to win. In our team, which is called loan servicing, we take care of the customer needs after their loan application has been accepted. And in that sense, our primary responsibilities are, one, we handle money movements, which includes funding of loans, collecting and distributing repayments from borrowers, and any reconciliation processes we need to account for all of the money. The second responsibility we have is we build tools which are used by our internal ops teams. Some examples of that are we help the payments teams with tools so that they can process transactions faster. And we also help our collections and recoveries teams with forbearance tools to help them service borrowers who are struggling with making repayments. So basically a couple of months ago, our product team came to this realization that our internal ops teams have a lot of these tools that they use to service borrower needs. It would be great if we could make these tools available to the borrowers, because the borrower know their needs best in terms of what tools will work best for them, what is it that they need at this point. It saves them a call to the customer service, and in doing so, it reduces operational cost. Having said that, we at Funding Circle, it doesn't mean that we don't want the borrower to call our customer service number. It just means that if they feel they can solve their own problems, they would have the tools to do so. That is the entire idea behind the borrower portal. So we were looking to build this out, and in the old way of building things, the way we would have to build it was part of this huge monolith that we had, which was based on your standard 3-tier architecture, which in our case is a Rails app. And because it is this huge monolith, you have this massive system with tightly coupled logic, all of our concerns in one place. And as a result of that, it took a really long time to deploy even small changes, because you would have this massive test suite, and it would take a long time to build for any change that we have. Another aspect of having a huge monolith is you would need to have heavy coordination between teams, which is sort of problematic because even for tiny, it just means that you have to coordinate your deploys in a way so that a large feature can be released without any issues. So initially, this is sort of how our teams look, which essentially mimic the design of our monolith system. And there were a lot of pain points associated with it. As you can see from the team, as you can see from the slides, the whole stack is composed of monoliths. So you have various teams working on a shared code base on the front end, and similarly a shared code base on the back end. But you had separate teams working on the front end and back end. All teams were working on the same code base, which meant there was like a very high chance that we were working all over each other's shoes. Because it was one backend and one front end, there was just one deploy pipeline. And to facilitate releases, we had a deployment queue. And so if we needed to coordinate releases, we would use this deployment queue. And finally, since this is a monolith, there is a high risk when deploying changes because we are deploying everything and we are making even like small changes. And even if it's like a tiny bug fix, we will be deploying the entire system, in which case there would be downtime associated with deploying. So certain, like, even if there was another subsystem that was entirely independent of the change that a particular team was making, that system would be down during the deployment phase. There were a couple of patterns on the backend that we wanted to try out so as to fix a lot of problems that we were facing. Our domain is loans is highly event driven. So one of the things we were trying to do was make our systems move more and more towards event-driven architecture. Together with a microservices-based approach, this would allow us to have smaller systems, which would solve like the maintainability problem that we have. Additionally, if we go to the next slide, there were also concerns regarding our data model. Because of the way we had like just one data model for read and write, we realized, at least for the borrower portal, our read and write workloads are very asymmetrical with very different performance and scale requirements. So we needed a way to solve that, and a unified data model, which the Rails architecture describes, would not necessarily work for this problem. We also had this issue of like when your read and write workloads are trying to access the same piece of data, there would often be data contention, and you would have to design the system to handle these kind of issues. Also, there were like performance-related concerns because the traditional 3-tier architecture can have a negative impact on your performance because your read and write workloads work together, and this also increases the sort of complexity of the queries that are required to retrieve information, because your unified data model is trying to simultaneously optimize for read and write, which is problematic. And finally, there was this additional concern of security and permissions, which we needed to manage, which was turning out to be very complex for all of the entities all of the data entities we had, because for certain objects we needed only read permissions, but because of the way the 3-tier architecture works, you would have to provide them write access as well, which was sort of a problem for us with the borrower portal. So yeah, I mean, another design together with the event-driven architecture and the microservices that we were sort of planning to use because it worked really well for a problem with the borrower portal was the command query responsibility segregation, or CQRS for short. CQRS, as the name suggests, tries to segregate commands and queries. What are commands? Commands are things that we use to update data, and queries are things, let's call it things for now, that we use to read data. So some general guidelines around how commands and queries need to be designed. So first, commands should be task-based rather than data-centric. So in our case, one example could be make a repayment instead of mark a particular repayment status as paid. Commands allow for easier asynchronicity, which means you can place them in on a queue and then have them be processed later asynchronously, rather than try to process them in this asynchronously as a part of your request response cycle whenever an HTTP request happens, for example. And on the query side, queries never modify the database. That is the one guideline that CQRS has for queries. You can have, whenever you query for information, it just returns a JSON-like structure in our case, which may or may not encapsulate any domain knowledge. Over here, we look at like a very generic view, very generic representation of the CQRS design pattern. So when a client wants to read, wants to get some information on the UI, they go down the query branch where the query hits the read database, which could be a materialized view, could be an entire a separate database, and this retrieves the data and shows it on the UI. Similarly, if there were some task that needed to be done, then that would update the data on the backend. Then that would follow the command branch, which would hit the right database to update the state. And there would have to be a system between your read database and your write database, which will sort of keep the two databases in sync, which is marked by this arrow that you see, which is called eventual consistency. Eventual consistency is not as fancy as it sounds. It is something that we have all seen in our daily lives. An example would be just like basically if you have a credit card, then when you're paying off your credit card balance, that could be an example of eventual consistency. What I mean by that is when you pay off the balance on your credit card, the money goes off your bank account on, say, on a particular date, but the balance is not updated for another 2-3 days because of the internal processing that the credit card company needs to do. So in the meantime, during those 2 or 3 days, you just see a message on your app or website which says basically that we've received the money, but we haven't updated your balance. So it will just give us some time, 2 or 3 days to update that balance. And after 2 or 3 days, you will see that the balance has been updated after the payment has been processed. So yeah, if we go to the next slide. So some of the benefits of CQRS that we are seeing with the borrower portal are independent scaling. So because we were able to separate out our read and write workloads, we were able to utilize these separation to scale these workloads independently. So in our case, for example, because this is the borrower portal has an API server which gives access to all borrowers to access the data that they need. Our reads were much larger than our writes, so we could horizontally scale the read layer much more than we needed to scale the write layer, which was very useful for us. Another benefit that we saw was optimized data schemas. So because we've separated out the read and write workloads, and because we've separated them out, we can optimize the data models for each of the two problems separately. So you can have a schema which is optimized for quick querying, while the right side, while the right side can have its own schema, which is optimized for quicker updates. This also solves the security problem that I was talking about earlier, which is you can have the right domain entities have access to the right workloads or the right data models, which would take care of like the right entities only have access to the read database, and similarly, the right entities have access to the right database data store. And finally, there is like a clear separation of concerns by segregating the reads and writes. You can have models that are maintainable, that are flexible, and that are handling the independent concerns by themselves. Most of the complex business logic, which when you're working on the unified data model in the 3-tier architecture, sits in the controller, but now it can sit squarely on the right side, like the right workload side of the logic. And the queries, like the read model can be still very simple because the queries are simple, which leads us to a final point, which is simple queries. By optimizing the read data model to fit the needs of the APIs or the queries, you can have a data model that is very that is optimized for it, and hence you would have like very simple queries on the backend, and your API access layer looks very easy. So after we talked about the benefits, let's talk a little bit about the challenges. So the first one is you have because of these additional things that you've added to the system design looks a little more complex than your standard 3-tier architecture. But it also means that you have added more components. That means you have more points of failure in the system. But in our case, this complex design is seeming to work out, as in we can manage the failures and all of those independently, which is nice. Another aspect of CQRS that is not necessarily a CQRS concern, but is often tied together with CQRS, is this whole idea of dealing with messages. So in our case, we chose to decouple the write systems and the read systems by introducing a Kafka infrastructure that we already had in place and utilizing that, which solved our problems related to asynchronous processing, and at the same time creating a read data model that works very well for our read workloads. And finally, I think the most important point when trying to work with CQRS is the idea of eventual consistency. If we have a separate read and write database, that means there is often a chance that the read data may be stale. Therefore, you need a system that will try to sync your write data into your read model, and it can be difficult to keep track of how out of sync you are. But if you are able to manage that, then in most cases, eventual consistency is not a problem, as we saw from the credit card example earlier. But it should remain an important consideration when you're deciding to choose CQRS. So finally, if we look at the way our current borrower portal is designed, on the extreme right, you will see there are these applications. These applications are our internal systems, some of which are monoliths, some of which are microservices. And all of these are bidirectionally interacting with the borrower portal, which is in this blue box, via Kafka topics. So if we go from right to left, we see that there is this component in between, which is called the API state generator, which is reading data from the various Kafka topics to populate it into the API DB. And your API server reads from the API DBs whenever there are queries. So whenever there's a query from the front end, for example, there is a borrower and she's logged into the borrower portal, and she's trying to get the state of all of the loans that she has with Funding Circle. So when she logs into the borrower portal, she makes a query to the backend, and that query hits the API gateway first, which is hosted on AWS API Gateway. That API gateway has a custom authorizer component, which will authorize whether this is a valid request or not, whether the entities, whether the loan entities that that the API is trying to access, does it have the right security authorization and all of those things. And if all of those are valid, then we hit the actual API server and get the data from there. So when we hit the API server, get the data from the API gateway, and the query then percolates back to the front. Once after seeing the data, she realizes that she's late on one of the payments. What she can then do is there is a button on there to make a payment. And once that payment happens, we then go down the command route, which is from the API gateway through the authorizer to the API server. But instead of hitting the API DB as you would in your normal 3-tier architectures, you directly publish a message on the Kafka topic with the relevant associated data for making a payment command. And then the backend systems, internal systems, will take care of basically consuming that message and processing it so that the payment gets marked accordingly. So, for example, our core servicing engine could receive this message and mark the particular repayment as paid from its late status and remove the overall late status on this particular loan. Our ledger system can keep track of this transaction that happened and therefore account for the new money that has come in. And finally, these internal systems will therefore publish their own messages back on the Kafka topic, which the API state generator will read and publish to the API DB. So the next time the borrower logs in, she will be able to see that this late payment that she's made has been processed and the loan is no longer late and she's caught up on her repayments. So what has this given us? So if you move to the next slide, as a result of building things in this new way, we were able to structure our backend teams in a slightly better way. So as you can see, we have this unified Kafka infrastructure, but each team can decide what data sources should power the APIs or should power the APIs and their processing independently of other teams, which has allowed each team to sort of build their tiny backend systems. And as a result, this allows the teams to have less coordination between them when they're trying to release features, as in, for example, backend team C can release its feature upfront behind a feature flag. And when backend team A is ready, they can release their their dependent version of the same feature. And when the two teams are ready to go live, they could just disable the feature flags that they have and the system, and the feature becomes live. The new way of building, so what has this helped us do with? We no longer need a Rails app. We can choose the framework that works best for the problem. We do not have tightly coupled logic. Instead, now we can start to design systems that are decoupled. We no longer have all concerns in one place. Instead, we have single responsibility subsystems that are focused on solving one problem and doing it well. In the past, it used to take a long time to deploy changes, but now, since we can break a system down into smaller subsystems, smaller subsystems means less tests, and therefore faster deploys. And finally, there was a need for heavy coordination between teams, but now you sort of need minor coordination, and things can be released behind feature flags, and then those feature flags be disabled when everyone's ready to go live. So as we can see, breaking things down has helped us tremendously on the backend. Now my colleague Alex will talk us through some of the things we are trying on the front end for the boilerplate.
Thank you, Sagar. What about the front end? At this point, and after all the changes that have been done in the back end, the front end, as we can see, is still a monolith. The main points with this are the same code base. So it's still a monolith, one code base. There is no defined ownership. So different teams working independently on the code base without any defined ownership, which can lead to code conflicts when two teams are working on an overlapping feature. Also, because teams have different roadmaps, alignment between the teams' roadmaps is a must. However, this requires a much bigger effort, and it's not possible at all times, reducing the speed of delivery. One single code base means there's only one deployment pipeline, which leads to the need of having a queue to manage this deployment pipeline. This can create dependencies between deployments. And each deployment, and because all the code is being deployed all the times, is of high risk, as something can break when rebundling all the code. The idea was, how can we change the front end to mitigate these pain points? So basically what we would need to do would be split the code base into smaller parts, assign parts of the domain into teams, so each team is fully responsible for each one of those parts. Different objective, so roadmaps per domain's part, has each team is fully responsible for a part of the domain. And because features that span across several parts of the domain are more rare now, the teams will work independently from each other. One single deployment pipeline has the code base will be split into smaller code bases across multiple teams. And because each team is responsible for a part of the domain, they can have their own deployment pipeline, mitigating the need of a deployment queue. Even if the queue is needed, it only contains deployments inside that team. So smaller independent deployments inside a code base, as the code base is split into smaller code bases, each deployment only has code for that same code base, making the deployment process less risky, because only that code base will be deployed and not all other code bases. This will lead us to this structure after mitigating each one of the pain points. Now, a whole domain is split into several other smaller parts, so subdomains that would be independent of each other. As we can see, each subdomain would be assigned to a specific team that would own the repository, define their own pipelines and infrastructure, and define their own roadmaps. If you look at this structure at this point, it starts to look a little bit like micro frontends structure, where all micro frontends are independent of each other and can be publicly accessible by simply assigning a URL into the production environment. So taking a look at our diagram, our high-level diagram, we would have this. We would have a front end per team representing a subdomain. However, this structure would lead into a scenario where a lot of the code, like the vendors libraries, the UI libraries, would be duplicated into each micro frontend bundled files, making the users to have to download it every time they would access a micro frontend. For example, if a user accesses subdomain A, the vendor's code, and all the UI libraries, and in our case, the vendor's code is React and React DOM, would be downloaded and parsed. And if then the user navigates to subdomain B, the same code would be downloaded and parsed again, as this vendor's code would be on each subdomain or micro frontend bundled files. What have we done to deal with this? So since we were already using Webpack to bundling all the code, the JavaScript code, we have also taken a look at Webpack's Module Federation plugin. What the Module Federation plugin allows us to do is having a JavaScript application to dynamically run code from another JavaScript application. So this allows a micro frontend to expose modules and to reference other micro frontends as remotes. So remotes is other micro frontends where they want to add modules from. In a more practical look, what the Webpack Module Federation plugin allows us to do is have our borrowers accessing our portal, which is by itself a micro frontend and is the only publicly accessible micro frontend. We then have all other micro frontends, with each representing a subdomain, exposing their apps and components. Then we have created a component which we called, well, micro frontend component that will load a specific module being exposed by one of the other micro frontends. However, a lot of the code is still being duplicated, as all micro frontends have in their bundles the vendor's code and the UI library code. To remove this duplication, we have created a shared micro frontend that will expose all this code, and where the micro frontends, after setting this shared micro frontend as a remote, can dynamically load the code. One other thing that the Module Federation gives us is the possibility to share several versions of the exposed libraries. As an example, the shared micro frontend can expose several versions of the React library, allowing the micro frontends to load different versions of the libraries they depend on. So with this in mind, and coming back to our high-level diagram, we get this structure. So we have a main portal, which is the public accessible micro frontend, and then each team can have their own micro frontend and be responsible for that. With all these changes, the main benefits that we are starting to see is team organization. So each team owns the micro frontend and has all the knowledge of it. As teams are independent of each other, they can now define their own objectives and roadmaps. There will be times where teams will have to align the objectives and roadmaps, but these will be the exceptions and not the norm. And each team can now configure, manage their own CI/CD pipelines according to their needs. So you can have different pipelines per micro frontend or per team. Regarding the code base, with the sharing of code, it makes each code base smaller and cleaner, as it will only contain the code specific to that micro frontend. Adding code splitting to each code base will make the code to only be downloaded if requested by the user. So just when the user goes to that part, that code is downloaded. With this, we see a drastic reduction of the amount of code that is downloaded by the user browser. In our case, around 250 kilobytes instead of megabytes. As the code bases are smaller and the changes specific to a code base, the deployments are smaller and the risk of breaking something on another micro frontend is reduced. Also, teams can also choose which client-side frameworks to use, React, Svelte, Vue, or any other client-side framework. And this is possible because all of this orchestration is done by the building tools when building the files. So the only requirement that the code bases have is the need to use Webpack and the Webpack Module Federation plugin. And also, if one of the micro frontends is down, this will not affect any other micro frontend, as they are all independent. This makes it easier to ensure that all other micro frontends remain stable, as they are all independent. However, after all these benefits, there are a few issues that we will need to keep an eye on. So we do have a more complex structure, as we now as we are now combining multiple applications, it may take a little bit more effort to debug the origination of an error. Not just one deployment pipeline. So each micro frontend has its own deployment pipeline, which creates more overhead maintaining them. And blind spot. So micro frontends can load components exposed by other micro frontends. And there is no list of which micro frontends uses which components exposed by which micro frontend. So this can lead to a problem if a micro frontend does breaking changes in one of its exposed components. However, to migrate this, all changes will need to be backwards compatible and using a warning message system, and every change needs to be clearly documented. So if a micro frontend is making backwards compatible changes into one component, they need to be communicated to the other teams. So again, coming back to the high-level diagram, we now have vertical teams, multiple skilled teams that fully own a subdomain. So we no longer have front-end teams and back-end teams. So we now have one team that owns the whole subdomain. So from the front-end to the back-end, middleware, whatever. All sections, front-end, back-end, and data sources are now split into independent, smaller code bases, making them easier to maintain, and smaller systems with lower risk of breaking something and lower deployment times. Yeah, so basically this is the micro frontends, and this is now the whole system.
And that brings us to the end of our talk. Thank you everyone for listening. If we are hiring, so if you're interested in working on the borrower portal or in general or in what we do, then feel free to pop into our booth, virtual booth at Funding Circle during lunch or whenever. For now, if you have any questions, Alex and I will be more than happy to answer them for you.
Yeah, that was wonderful. Thank you very much, Sagar and Alex. Very insightful into what you're doing, moving from a monolith to microservices. So we have a couple of questions that have come through already. So I'll go through those, and then if anyone from the audience has any additional questions, please do get them in the chat. So first up, I've got a question. How will the borrower portal help your customers with obviously the changes that you're making?
I think so we have all of these tools internally that a borrower needs to call the customer service to get access to, right? So for example, if a particular borrower is late on their payments, or if they want to early settle on a loan, as in they don't want to wait the entire 5 years to make repayments if they have a large sum of money at this moment and they just want to pay it all upfront before the end of term of a particular loan. At the moment, what they have to do is call up customer service and agree on certain things, right? So for example, in the case of early settlement, they would have to agree that this is the amount that they need to pay. With this tool, when this tool becomes available in the borrower portal, what the borrower can do is simply look at this information on the portal and be like, okay, if I am able to make a payment by this date, then this is the amount that I need to pay. But if I am late by that date, and if I choose to pay after this deadline, then this is the amount that I need to pay, and then decide what works best for them. So basically the information that they would have to call customer service for, we are releasing that information slowly in an iterative manner to the borrowers so that they can make a more informed decision rather than having to call up the customer service.
Wonderful. Yeah, makes a lot of sense. And then what is the greatest challenge you faced so far whilst creating the borrower portal?
I think so. I can talk about some of the challenges we faced on the backend, but I think Alex, and then I'll hand over to Alex to talk talk on the things fronted. So from a backend perspective, this was sort of the first time we were doing something like this on the servicing side. So, like obviously, the technical know-how of how to interact with Kafka and all of those things, plus which topic become your sources of truth, was like that was sort of like a difficult problem to solve for. And if if the data that you need is not available in certain topics, how do you make that available? Like basically getting the data you need for the portal by not directly interacting with the core engine, the core servicing engine, right? The data is available in one place, you need it in some other place. How do you get the data there? Those were sort of like the trickier problems we needed to work through.
Yeah.
Regarding the in the front end side, I think the biggest challenges were decoupling all responsibilities. So which responsibility belongs to which micro front end, and also this is all still very new, this module federation. So there are still a few things that we are keeping an eye on, and we are actively working to solve. One of them is testing, the unit tests and all that, because has all of the code is being, or most of the code is being shared. So we need to contemplate that on the testing builds. So those are the biggest challenges on the front end.
Yeah, makes a lot of sense. And then I guess links to challenges is how do you ensure that you're not duplicating both data and logic in the various microservices?
Yeah, I think that's a really nice question, and we are sort of facing some of this ourselves. What seems to have worked for us at this moment is not to worry too much about the reuse side of things. If there is some duplication temporarily, we go ahead with the duplication and then figure out how we can reduce the duplication instead of like over architecting the system, over designing the system initially. And then once you see sort of the patterns of duplication, you can probably pull that out, make its own system, and use that data like through Kafka topics in our system, right? Or use that system directly. But at the moment, we have just gone with, if there's a duplication of data, we're fine with it. Let's revisit this in a few months' time and see if we can see any patterns of duplication.
Yeah, absolutely. And I guess that really links also to how you can ensure to maximize the reuse of capabilities as well, right, in the microservice as well?
Yeah, that's true.
Absolutely. So onto a few questions from the audience. We've got a slightly general question to start. So either of you can jump in on this one. How do you develop your soft skills as a tech, especially whilst working from home?
I think if you have a team that is ready to interact and you sort of have that vibe going on within the team, which I think is sort of one of the better aspects of Funding Circle, it just becomes easy to work through the soft skills by just interacting with the team, right? So if you have a problem, then you communicate with the team, and that sort of helps with like communication skills. If you have competing ideas and then you sort of have to figure out what works best, then there's the idea of just like having a proper discussion, both sides asserting what are the good and bad points of each of the competing ideas, and then sort of coming to a consensus, which I think again helps. And similarly, like pushing back, like all of these things just happen by having a proper culture, having like a good, healthy team culture, I think.
Yeah, absolutely.
And just to add to that, a lot of online sessions also. They are needed, yes.
Yes, online sessions, a lot of team building. Absolutely. And then combining a couple of questions from the audience as well. There's a few a few overlaps here. What tech stacks do you guys use, both sort of front and back end, and also what sort of training do you have to upskill for junior developers internally?
Tech stack wise, as I mentioned in the talk, our old monolith system is primarily Ruby on Rails based, but like with the newer event based thing architecture that we're going with, we've sort of added this Kafka layer in between, which becomes like your source of a lot of information, and then you can almost choose what framework works for your problems. But generally, in our case, on the backend side, we've gone with a Ruby because like a lot of the teams are familiar with that language, and in some cases Clojure because it's a functional programming language, but at the same time, it has like a nice interop with the JVM on which the Kafka, like the whole Kafka infrastructure works, and the Kafka Java library is like the best version of interacting with Kafka. So those are the two we've sort of settled on the backend for now.
Yeah. For the front end, we went pretty much with the common stack for the common parts, so the portal micro frontend and the shared micro frontend, which is React. We're using React hooks. In one of the micro frontends, which we also used React because we are getting the code from the shared micro frontend, we are also using React context for the state management. And the good thing about all this structure is that each micro frontend can choose their own stack, the stack that better serves to create the solution for their problem. So yeah, we can recommend React because we have already some things done in React. But if people want any other client-side framework or any other tools, yeah, they can choose for it.
Makes a lot of sense, a lot of flexibility. And then a very interesting question. Here we go. What's the deployment environment that you guys use? Are you on AWS, Azure, GCL, or is this?
I can go first on this one. For the front end, we are using AWS. All the micro frontends are being deployed into an S3 bucket with a CloudFront instance in front to cache the files. That's pretty much it.
Yeah, and on the back end as well, like the main deployment environment is AWS. We use AWS API Gateway for our API Gateway layer, and internally we use like the EKS Kubernetes cluster, which is managed by AWS for us, and we deploy all of our code on this Kubernetes cluster, and essentially like provisioning of resources is done through like Helm, Kubernetes, and Terraform for like AWS services. And finally, like the Kafka infrastructure is hosted on Confident Cloud, which DevLabs or invented Kafka, and that has access connectivity with our EKS clusters. So that way the connectivity is maintained.
Okay, thank you very much. And then we got someone who would like to know a little bit more about the API database and its position in your architectural design.
Yeah, sure. So the API database is a read-only database. So the state generator will write to this database from various Kafka topics, but it is optimized for read queries, and so any API query coming in from the front end will just be like, okay, get me this data for this particular ID, and that would just be sent to the front end as a JSON structure, which the front end can read and use.
Perfect. And then another sort of process question. How's your model layer defined?
So yeah, on the API DB side, it is defined to make it easy to construct the JSON that we want to send to the front end, right? So in most cases, it's just get the JSON for this ID and send it to the front end. which makes it very, very easy to just query information. On the back end, on the right side, basically, like a lot of that data layer is a relic from like the 3-tier architecture systems that we have. So a lot of those are like monolith systems, so they have their own data layer, which is slightly complicated because you have your read and write concerns happening simultaneously. But yeah, we're slowly trying to move away from that.
Sure. And then we've got just a few more questions, sort of more generalist about sort of Funding Circle than sort of what you're individually doing. But one of the questions is around sort of how often you sort of expand and recruit in the software development teams.
Oh, I think we're almost hiring all year round. Like we've been growing a lot, and so we've constantly had to like hire more and more people in product engineering, in data engineering, platform teams, infrastructure. Like I think we're hiring quite a lot.
Brilliant, yeah. And then for anyone who's interested, I guess, join the private room afterwards, and you can go through obviously all sorts of progression opportunities, and ask any questions directly to the team about sort of live opportunities at the moment.